So now we are going to switch gears a little bit. Instead of introducing yet another method, we will finally take a kind of an application where some of these methods would get used. And the application that I will pick is something which is most commonly found in engineering. These are called least squares problems. Okay. So for those of you reading the book, this is chapter 10 of NPTEL, right? Okay. So let's start this discussion with an example. Okay, a very, you can say real life kind of an example. So let us say that there is some, for example, a nuclear reactor in Japan which is melted down, right? And you go with a Geiger counter and you want to measure what is the kind of radiation coming from there, and you want to model it. So you can see that if I can get a model of it, of the radiation coming from a destroyed reactor, that will be very useful, because if that model is accurate, you can predict until what time is it going to be unsafe, until what distance is it unsafe, and all those kind of things. So these, so this model, for example, could be some very simple, like so here x is not space, x is some parameter that I don't know. So what is it looking like? We know that radiation decays exponentially, right? This, if you remember the very first lecture of this course, we said there is a optimization begins with a modeling phase. And that modeling phase does not come from optimization, that comes from your core expertise, whether it's nuclear physics or chemical engineering or whatever, right? So the nuclear physicist said that radiation has an exponential decay. Now when I say exponential decay, immediately, without being a domain expert, this is the most general model I can write. There is some offset at time t, there is some offset, I call that x1, and there is an exponential decay which has some weight x2. And the rate at which this decay, that's yet another variable, that's x3. This is about as general as I can write. Now, what is going to be, as someone who knows optimization, what would you want to do? You'll go with your counter. You will make several measurements, right? So you will measure, let's say y1 at what? Time t1. Then you will measure the radiation y2 at time t2, okay, and so on. So these are the knowns of the problem. Now as I am making these measurements, what are the unknowns? x1, x2, x3. Do they change with time? Hopefully not. So the more general way of writing this is that at times ti, I is equal to 1 to m, measure yi, I is equal to 1 to m. So I get m measurements. Now having gotten these measurements, what is our job? Give me the model that explains the measurements in time, right? So come up with a model. Now supposing I do come up with a model, what would be a sensible way to test how good the model is? Like what is the measure of goodness of the model? No, I am not asking how to solve the problem. I am asking you, having gotten a model, let's say you got a model, how would you assess whether this is good or not? Does the model prediction match the measurement? It will not. So how do I then quantify, in real life problems it will not match. Why? Experimental noise, measurement noise is always going to be there. You will never get exact match. That's obvious, right? So now that it doesn't match, how do I quantify this error? I could, some distance, exactly. I need some measure of distance between the two, right? So for example, I could do, so error measure. I could do, for example, I could compute this for all j's. Is there any other thing I could do? The hint is the title of the section. I could square it. I could look at this measure. I could look at yi minus y, oops. Okay. Any advantages or disadvantages? First function, the modulus function, is it differentiable? There's a problem at the origin, right? So if I start doing calculus, I may end up with a problem at the origin. The second one, it's nicely differentiable as long as y is differentiable, right? So that is one practical reason why I will choose this, okay? So this is to test how good my model is. Now how do I come up with the model itself? I have my measurements, right? And now in the language of optimization, how would I write it? All you have are the measurements. And we said that square of errors is a good way of measuring something. So language of optimization, I would want to, what to these sum of squares? Minimize them, right? So I would say that, for example, x hat means the optimum x is equal to r min. What is the variable? X, the parameters, right? And I have m measurements, so let me try to minimize the error in all of those measurements, right? So this is going to give me yj minus yx of tj. So if I find that x, so let's read this in plain English. Argmin means that x, which is the variable of optimization, which it minimizes the argument of this, right? That is my x hat. So I want that x which does this minimization. If I get this, I'm done. This is the x hat which explains the data very well. Why does it explain the data very well? Because when I insert that x hat, this sum of squares is minimized, which is what I want. So you see, in a very, very natural way, we have ended up with trying to minimize a sum of squares. So that's why these problems are called least square minimization problems. And this is virtually, I would say 90% of engineering is least squares optimization. Whether or not people realize it formally or not, that's what they're doing. Okay, so this is, hence the word comes least from here and squares from here. Now there is another small distinction that is made over here in least squares problem. Like we looked at conjugate gradient method, there were two flavors of conjugate gradient. What were they? Linear and non-linear. Similarly, there are going to be two flavors of least squares problems, linear and non-linear. This real life problem which I have written over here, radioactive decay problem, x1 plus x2 exponential minus x3t. Is this linear in the variable? Which is the problematic term? x3. x3 which is sitting in the exponential is not linear with respect to the with respect to the variables of the problem, right? So this is an example of a non-linear problem. Okay, so this is a non-linear, non-linear least squares. This is a non-linear least squares problem. This is of course going to be a bit more difficult to solve than a linear least squares problem. On the other hand, let's say that my model was something like this. right? This could, for example, come if I'm trying to model, you know, distance covered by a ball that is dropped. Maybe it should be something like this, right? U plus 80, whatever. So it will be a quadratic. So is this linear in T? It's not linear in T, but we don't care about T because T is going to be my measurement. T is going to be given to me. At time 1.1 second, I measured this thing. So in terms of the variables X, what is it? It's linear. It's X1, X2, X3, they're appearing by themselves. They're not multiplied by each other. They are not in log or exponential or whatever. So this is a linear least squares problem. Okay. Right. So this is as far as the introduction to at least the motivation of least squares problems goes. Okay. In the next class, we will look at now we have done the formulation of this, right? Once we have done the formulation, obviously the next step that we will do will be calculus on this, so that we can start our journey of minimization, coming up with a solution and then solving it. Okay. We will get two different cases for the linear and the non-linear, and we'll look at what happens over there. Okay. So those of you who are currently solving a research problem for your thesis, for your UGRC, for whatever, right? Go back and try to look, with high probability you will come across a least squares problem somewhere in your research. Okay. Alright, so I shall see you folks next